right, let's get started. So, good morning, everyone. Where are we at? We are starting module 3. So, this is going to be a short module, this session, next session. I just needed to fill in the blanks on a few things that I've left aside until now. By the time we're done with module 3, we covered actually, well, all the building blocks, of course, we've done that since module 1, but we covered actually all the different skills that you need to be able to write code from scratch. So write code from scratch is not just about coding, you know that now. It's about problem solving. So break down a problem into tasks that you can then implement into Java, for example. Okay. So skill 1 and skill 2, I regroup everything here under skill 1, like translating code, whether it's Java to English or English to Java. So what we've called implementing. Skill 2, code tracing. All of this is about reading code. Okay. So now what we are missing to be able to write code from scratch are 3 more skills. And 3 more skills in a week, that sounds maybe like it's rushed, but it's not. Because those skills, I'm going to explain a little bit more about what you should be expecting from them, okay? So the name of the skills are testing, refactoring, and debugging. So together, implementing, code tracing, testing, refactoring, debugging, those 5 skills are your foundation to solve any programming problem, always. Okay. Even when you learn more advanced techniques, you do OOP and stuff like that, object-oriented programming, you will still use those same 5 skills in a loop to be able to solve problems. So testing, we are going to talk a little bit about it. That's going to take us a little bit of time, okay? But the idea behind testing is that testing is I was going to say a science. I don't think it's a science. I think it's an art form, maybe. It's an art form on its own, okay? Knowing how to test software. Maybe you've heard of some friends that were working as quality engineers or quality assurance engineer, right? These are the people that actually spend their entire time testing software. So it's a big endeavor. That's what I'm trying to say. We are not going to learn to be Q&A engineers. What we are going to do is we're going to just look at testing as a way to guide us while we write code. You all played a little bit with coding bat, okay? You see how that table comes and tells you what works, what doesn't work in your program, how much of the requirement you are compliant with, etc. I never had anyone, and you can manifest yourself if you think differently, right? But I never had anyone come back and tell me coding bat is horrible and it hinders my learning. Never. Okay. As a matter of fact, we cannot use coding bat in COP2512 for a reason I explain when we get there. But students generally ask me, like, you know, it would be cool if we could have coding bat also in COP2513. So bottom line is that testing thing, it's meant to help you. So coding bat is going to scaffold you all the time. When you write code in an intermediary exam or at the final exam, you are not going to have coding bat to help you, but by then, the idea is that you played enough with coding bat, that you have seen, you know, tests and stuff like that. We talked about how to make tests in class. You are going to be able to generate your own. So it's another one of those situations where when you program alone, there's like, you have to split your brain in 2 halves, right? One half is writing the code. The other half is trying to find out a scenario. By scenario, I mean like a way to use the code that you just wrote that would break it. So you're constantly fighting yourself when you program, right? If you don't do enough of the fighting against yourself, then you just write code, you think that you did something great, you turn it on, you turn it back to the grader or to your manager or whatever, and it comes back as bad news, right? So we have to constantly try to do our best to break our own code so that we don't have to deal with other people breaking it for us as a student and also as worker in the workplace as programmers, right? So that's everything that testing is going to do for you. Provide you guidelines, provide you a concrete goal to achieve, provide you a way to make sure your code does what you think it's doing. Refactoring, that one is going to be super trivial. Honestly, it's like 3 slides, I think 4 slides maximum, and one of them is a title or something like that. So refactoring is actually a skill that allows us to tidy up our code, clean up our code. So one of the things that I want to debunk for you, like right off the bat, and I already started doing that, right? The illusion that you are going to read requirements and you're going to type code, type, and then you are going to compile once, and it's going to compile, and then you're going to run it, and it's going to do everything that you thought it was going to do, right? So I already kind of broke that myth for you. You are going to have to go little bit by little bit. You're going to have to make errors, correct from your errors. Well, refactoring says that even when you get to a solution, the first solution that you come up with, and by saying you, I mean everybody, me included, good programmer, bad programmer, etc., professional programmers, the first solution that you come up with for a new problem is 95% of the time, whatever big probability, over complicated. That's just it. You are busy trying to figure out how to solve the problem. A lot of ideas come to your mind. You try to tape them together, okay, with duct tape, and then you get something that works, but it's ugly, it's overcomplicated. You would be surprised by how much you can simplify code if you let it sit for one day. You go to sleep happy because your code is working. You wake up the next morning, you look at your code and you say, I cannot show that to my coworkers. So you go ahead and simplify it. Now you have a little bit of a setback. But the priority in this class, I've told you that all along, okay? The priority in this class is get it to work. I don't care if there is like duct tape, if you have like little pieces dangling, etc. No, get it to work correctly. Once your code does what the requirement asks you to do, then you worry about refactoring. You worry about rewriting the code so as to make it better. So what can be better than code that is already 100% correct? Well, code that's readable, code that's easier to understand when you read it, code that's easier to maintain, code that is less likely to have bugs, code that is more likely to be transformable in the future if you need to add more features to it, stuff like that, or even downright to code that runs faster. Okay, for us, it's never going to matter. We are not trying to optimize code to go faster. But if you're working in certain industries, like IoT, so for example, you want code that has a small footprint, a small memory footprint. If you're working in game development, you want code that is going to be able to react to those 60 plus frames per second, right? So this is when you are going to take all of that into consideration. But trying to optimize, trying to refactor before you have code that works, that's generally a bad idea. Okay, that's almost always a bad idea because you are going to try to optimize something that's just not working. Okay, so you have a broken down car without wheels and you're putting a wing on it to improve the aerodynamics. Good luck with that. It's not going to do much. Okay, last one, debugging. So debugging is as complicated, if not more, than just programming by itself. Okay, the good news is that the way that I'm going to introduce you to some basic debugging techniques, you're going to see that it's very similar to what you have learned to do to write code. So code tracing, is going to be relevant. Implementing is going to be relevant. Testing is going to be relevant. So all those skills are going to come together and we are going to use them slightly differently to help us debug our program. And when we're done with this, we are going to have a complete description of the programming thought process, how you need to think when you are trying to solve a programming problem. And it's different than how you have to think when you work on your physics class or how you have to think when you work on a discrete math class, etc. You have to adapt. This is what we're talking about here, the thinking process that you need in this class and in all the programming class to be successful. So we are going to actually start by that. I'm going to give you an overview of that, and then I'm going to fit those missing pieces in that overview, and then we are going to go through the missing pieces. So, learning activities for this module, we are going to have practice exercise. As usual, the practice exercise are given in the slides when they become relevant, so when we cover the stuff that allows you to do the practice exercise. And then we are going to have graded exercise on coding bat, where you are going to be able to apply that code completely from scratch set of skill. Okay, so more coding bat coming up. The links for coding bat are here. They are also in the module. So module 3 has been released sometime over the weekend. I don't remember when. You are going to find all the links directly to the specific exercise you have to complete. I've been running the auto-grading script in the background semi-regularly, so you should see your grade updated every few days or something like that for GE02. And when this one is active, which I'm going to probably make it active tonight, then you are going to start seeing your grade for GE03. Okay, so bear in mind that announcement that I put on Piazza. If you suddenly get a 0 for GE03, don't freak out. Okay, that's just the auto-grading script is looking. What did you complete? Nothing. Okay, so you get a 0 for that one. But as soon as you complete stuff, you're going to get your credit. Okay, and if you bump into problem, you don't get the credit, you know where to find me. Don't hesitate to post on Piazza in the technical support group. Okay. All right. So what is that programming thought process that I've been trying to sell you? Well, module 1, we covered all those building blocks. Okay, there are not that many. There are 6 building blocks, 3 types of loop. What else? We have to arrange them serially or in a nested manner. So there is a finite set of combination of things there. Okay, so nobody should feel overwhelmed there. If you're feeling overwhelmed, let me change the perspective that you're using to look at it, because I guarantee you, when you look at it from the right angle, this is not overwhelming at all. Okay. And then we talked about skill, programming skills. So how are we going to leverage those building blocks? We talked about implementing and translating back and forth. I put that together in one skill. We talked about code tracing, and we learned to do trace tables. And then I showed you last time, by the way, when you are in a hurry, okay, when you are in an exam, you're not going to do the trace tables. The trace table is training, okay? This is you getting the reflex, the mental reflex. You are going to use a debugger, you're going to use println statement, stuff like that we covered at the end of last lecture. And then there are those 3 skills that are just, described. I gave you a synopsis here real quick. Testing, debugging, and refactoring. And by the way, when we are testing, we're going to learn to do test tables. Okay, so these are just format of things that we write down. So now what we need to do, we just need to put it all together, okay? We just need to wrap it up with a bow and we're done. So that's the goal of this first series of 3 modules, M1, M2, M3, is to make you realize that programming is actually not overwhelming. Programming, yes, you can write an infinity of different programs in almost an infinity of programming language, right? But the fundamentals of programming, they're all there. Okay, for this class, the next one, the one after that, and that will follow you even in data structures. For 4 classes that you have programming, this is your target. This is what you need to develop as skills. Okay, so let's take a little bit of time to see how we are going to combine together. So the usual programming exam, like the final exam in this class, or the intermediary exam as we start intermediary exam 4, 5, 6, etc. I'm going to give you a wall of text, and I want you to pretty much produce some code. If you are like just taking a quick look here at the slide, the wall of text describes a program that is going to read positive integers from the user, blah, 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 compute a grade average, something like that. And you look at this has nothing to do with it. This is using syntax we didn't even cover. This is just a code that has nothing to do with the requirement. So of course, what we want to do is we want to avoid, just producing whatever code in response to the question, We want to produce code that is going to satisfy the requirement. That's been the deal all along, even like before we started very slow, right? So the problems that we have to do that, a few. The requirement, generally, they look confusing. And in real life, actually, real life meaning at work, or as you get classes that are upper level, like data structure, etc., the higher you go into your curriculum and eventually the workplace, the less clear the requirements are going to be. It's going to come to a point where if you ever are in charge of a project, for whatever reason, you have to develop some software, you are like either in charge of the project or you are like a senior software developer in your company, you are going to have to deal with the clients, the dreaded clients, and they are not going to give you requirements that are even remotely close to something unambiguous or that you could translate into an algorithm. That's just the nature of real-world communication, between professionals. So in this class, don't worry. We try to make them at least as unambiguous as we can, but I want you to keep that in mind, okay? Because ambiguity is part of the challenge. A programmer has to be able to adapt to that. As a matter of fact, software engineers are going to spend a lot of their time doing something called requirement analysis. Requirement analysis is just a nice way to say, these people are asking me to write some code, but the way they ask me to write some code, I don't even know what they want. So I'm going to write down what they say. I'm going to show it back to them. We are going to come to an agreement that this is exactly what the program needs to do. Then we are going to all sign off that contract. My team is going to work for 3 months. When we come back, the client is going to owe us money because we did what they told us to do. It has to be formal at some point, okay? It cannot be just vague. So we have those requirements that are even in this class, a little off-putting sometimes. So we have to deal with that. We have to make them a little bit more palatable, a little bit more easier to work with as programmer. And then we have to make sure that we don't write code. And then after 20 minutes of literally piecing of code, we try to compile it and it doesn't work. And then we try to run it after spending half an hour making it compile, and it doesn't do anything even related to the requirement. And that happens all the time. Okay, the students that have the most problem in a programming class are generally the ones that write a lot of code. They try to solve the whole set of requirement or half of it or a huge part of it. And then they realize, I don't even know if my syntax is correct. I don't even know if this is working, which part is not working. And then they get lost. Now you get overwhelmed. So programming is not overwhelming if you take it one step at a time. If you go too fast, yes, it can be like quicksand. It can be very overwhelming, very fast, and then you don't get out once you are trapped in that kind of loop. Okay, so I'm trying to prevent you from falling for this. So to prevent you from falling for this, we have a method. There is a method to this madness. So what we are going to do is we are going to use the requirements as our target. That's the goal of requirements. Requirements in our course, that's, for example, the description of an exercise, the description of what you have to do at the final exam or something like that. In the real world, this is what your clients tell you. What we are going to do from those requirements is we are going to extract both features and tests. What does that mean to extract a feature? That means that I don't want to look at all of this. I'm going to read it once to get an idea of what they want, like the big picture, right? But now that I have to start writing code, I'm going to try to find the smallest piece of requirement that I have an idea on how to write it. That's helpful, okay? And I'm going to take that little piece of the requirement, run away with it, and make it work. For example, write a program which keeps reading positive integers from the user representing grades, sums them, and keeps track of how many values are entered. Please not, whoa, hold on. So I read that to get the idea. Okay, this is about entering grades, etc. Now, what am I going to do? Write a program. It's stupid, right? This is the smallest building blocks that I can find. I use the term building block. I'm going to use it a little bit more freely than what we define in module 1. What I'm looking for is there anything in that block of text that I've seen before? Either one of the 5 building blocks, or maybe an exercise that I understood from the slide, or maybe an exercise that I remember writing, for example, a counter control loop that goes 1 to 10. That can form now in your mind a pattern, kind of like a larger building block, right? So you are going to look in that for small pieces that you have done before. The one thing I'm like 200% sure everybody has done before in this class is write a program. What does this entail? Open JGraphs, create a new file, give it a name, write the class declaration, write the main declaration, and then wait and see what you have to do next inside of it. But you know what? I'm going to treat that as my first milestone. Why? Because if that doesn't work, everything else is crap. If I write a class definition and my class definition is not properly written, there are syntax errors, or the name of the file doesn't match to the class definition, what am I going to do? I'm going to make mistakes, and then I'm going to pile up more code on the mistake, and I will have to deal with those mistakes sooner or later. So instead of just piling more code on top of bad code, I'm just going to write like a very basic empty program in Java, but I'm going to make sure it compiles. And I'm going to make sure that if I run, of course, it's not going to do anything, but at least it's not going to crash for whatever reason, like the JDK being badly installed or something like that. That's the level at which I want you to operate. You isolate, write a program, you take it, that's my next feature. My feature is I will have an empty program. And then you are going to go through that cycle, you're going to make sure it works, and you are going to think also in terms of when am I going to know that it works? Well, I already told you what I was going to do. I'm going to compile it. For this, there's not much to do, right? I'm going to compile it, make sure that it has no error, no warning, and then I'm going to run it, and I expect the program to do nothing, but I expect it not to crash. And that's it. I have extracted a goal, I've extracted a feature, and I try to find something that I've seen before in one form or the other that I can adapt pretty much to do. And then I take this and I go through the cycle. The first cycle, how am I going to make this work? So let's write a program, but because it's not that interesting, but let's say that I got that part working already. And then I read here that I need to read positive integers from the user. What do I need to be able to do? I need to read integers from the user. Later, I'm going to make sure they are positive, but right now I need to read integers from the user. That's my next goal. How am I going to test it? I'm going to run my code, make sure it compiles, run my code, type a number. I'm going to decide, for example, I will enter 42, okay? And then I'm going to make sure the value 42 was read by my code. How can I do that? Just by printing it or using the debugger, okay? Whatever way you want to go, but I have a plan. I know what I need to do, read an integer from the user. I know how I'm going to test that this is completed 100% and works. So now, design hypothesis. Design hypothesis is a fancy way of saying, how do I do this? How do I implement that that tiny little feature that I selected? So I'm going to just remember that I learned by heart how to read an int from the user. I need to import a scanner. I need to declare a variable and initialize it of type scanner. I need to use that variable to call the nextInt method. And then whatever that call to the method nextInt returns, I need to store it in a variable or use it, whatever I want to do with the value. So this is my plan now. This is my hypothesis. Now that I have an idea of what I need to do, I implement it. So now that I have an idea, I have identified a building blocks or a series of building blocks that are going to help me get that task done. All I have to do is translate them. Okay, I have a vague idea in my mind. I'm going to translate it in Java code. That's what we have been doing, implementing. That's easy. That part of the skill is easy, right? And then once it's implemented, I compile it and I run it. And I run it against what? Against the tests that I thought about when I was extracting the feature. So you'd better write those tests down on a piece of paper, right? Otherwise, you're going to forget. You need to keep a list of all the tests that you think about. So it's very good to have a piece of blank paper next to you when you program, right? And I'm going to, now that I have implemented this code, I'm going to compile it, run it, and I'm going to enter, what did I decide? I look at my test, 42. 42 was the number I decided to enter. I enter the number 42. I check that 42 was indeed read and assigned to a variable using the debugger, for example, or just having a print ln statement. And then, at that point, my program is working. It's doing what I set to do in the beginning. I'm going to refactor it. I'm going to clean it up, tidy up, see if I can improve it. So this is not adding any feature. I'm still just reading an int, right? But this is trying to make my code better, more readable, more usable. And then rinse and repeat. And that's it. That's it. So if you look at programming as requirement, I need to produce this output. That's not how to learn programming. You look at programming in terms of, I have a block of requirements with a bunch of features here that need to be implemented. And now I have a process to extract one feature at a time, implement it, thoroughly test it, make sure it works, improve it, polish it after it works, and then only go to the next one. Guess what? This is going to make programming actually more enjoyable. This is going to make actually easier for you, make it easier for you to get partial credit. Because now if you, for example, if you have a 2-hour exam, you go through one feature, one micro feature, another one, 2, 3, 4, 5. You haven't finished the code, but you have 5 of those features implemented. If you do that correctly, you are going to get near full credit for those 5 features. Maybe there's a little bit of an error somewhere. That's okay. But at least it compiles, so you don't get a 0. And then it's actually, according to your own test, it's actually doing what it's expected to do. Maybe you forgot to test something. Okay, you lose a few points. but most of it is in your test already. Most of it is working. You are raking up the points. So it's not just about raking up the point. It's because that method helps you as student. It helps you as professional. It's the way. It's just the way, right? It's the way to actually write code in a formal way, in a professional way. Okay. All right. So that's it. That's all there is to it. Except that most of the time things do not go well. So that means that when you go and you test your code, well, you didn't write s.nextInt. You were thinking about an old program that you saw in the textbook or whatever. You wrote s being your scanner, let's say, s.next double. So now when you type an int, what you get is a double, and the double displays differently on the screen. Bottom line is you have an inconsistency. You expected your code to behave a way. When you run it, you observe that it behaves a different way, right? That's called failing a test. So first part, we assume the test was passing. If it passed, I polish my code, go to the next feature. If the test doesn't pass, you're not giving up. And this is a hard rule, okay? I mean, that time, sometimes you are so stuck that you have to give up, backtrack a little bit, try a different feature, come back to that one, okay? That's real world. Real world is messy. But ideally, when a test fails, you do not give up. What you do is your problem. I wrote code. I thought it was doing this. I look at the code running. It does that. Guess who's wrong? It's probably not the computer. It happens sometimes. I found bugs in standard libraries at times, but this is really rare. It happened one time in my life, right? So this is, most of the time, this is you. So you have to come to terms with the fact that you were thinking that your code meant blah, but it meant something completely different. How do you figure out? You trace. You go through your code step by step. You understand how the computer executes your code, and you understand why the computer ends up doing that thing that you didn't expect it. When you see the computer do that thing that you didn't expect it, which can be, for example, iterate in a loop one too many times, okay? Or multiply by 2 the result, even though you had already the correct result, and now you're multiplying by 2, what the hell is going on? Once you identify the exact step of the code where the program diverges from the expected behavior, okay? You look at it, you take a very close look, and guess what? Your job now is to remember that particular scenario. When I put in 42 in my code, it crashes. So that's going to be a part of my test now. But it's also a test where I'm going to write down, this was a bug. And hopefully I'm going to resolve the bug now because I see the part of the code that is doing something wrong, right? But I'm going to keep that test because in the future, if I try to add more features to my code, if I try to be fancy, etc., I still want to make sure that I never go back to that bug again. That's called regression testing. That's called making sure that as you add stuff to your code, you are making progress. You are not regressing, Like Monday morning, I had this bug where my code crashed if you put in 42. Tuesday, I fixed the bug. Wednesday, I added a feature. Thursday, I added another feature. Friday, I added another feature. I'm ready to submit my code. I just run it and type 42. It crashed again. Crap. What happened? Regression testing failed. Okay. You should have constantly, as you were implementing new features, you should have made sure every time that you didn't break something that broke before. So that's why we keep that list of tests, right? So we are going to put in our test not only tests that helps us make sure a feature is implemented and works, but also tests that have been causing problems in the past so that we're sure that those problems do not reappear in our code. And once this is documented, once I have documented that when I type 42, my program starts whistling, there's smoke coming out of the screen, and then it crashes and burns, now I'm back to designing an hypothesis. What does that mean, designing an hypothesis? That means that I was tracing line per line, okay, line per line, and I found the if statement, for example, where I expected to trigger the first part of the code, but for whatever reason, my condition was false, and I ended up executing the else. That's where it's not working. That's where it's taking the wrong turn, right? I expected my code to do this, and it does that instead. I'm looking at that if statement, I'm looking at that condition, and I'm starting to think, why is my condition false right now? It should still be true for this present moment, right? So what in my condition is leading it to be false? Why are those variables holding those values right now? Did I make a computation error before, etc.? You are going to brainstorm this, and you are going to come to a conclusion. For example, you know what? I don't know what I was thinking. It should not be, for example, x lesser than 50. It should be x lesser or equal than 50. I'm just picking up a random statement, right? So now you are making an hypothesis. Okay, I think I understand why my program does what it does, but I still want it to do something different. So now here's my hypothesis on how I'm going to change the existing code so that it does what is actually planned, what is needed in the requirement. Once you have an hypothesis, what do you do with it? Basic science, right? You have an hypothesis, you test it. So you're going to implement it first. I forgot about that part. You're going to implement your hypothesis, so you're going to change your code, x less or equal than 50, and then you have a new version of your code. Test. The same test. Actually, not only the same test that was posing problem, and hopefully now you pass the test and you go here, right? But if you don't pass the test, your hypothesis was wrong. Back to the drawing board. Trace again. Understand why the program does what it does. And then change it, rinse, and repeat, okay? And do that until that test that was failing passes. And what do you do when your test finally passes? You celebrate, but don't forget, you have a list of 5 tests maybe on your list, right? Regression testing. You pass the one that's the most recent bug that you discovered. Make sure that your bug fix here didn't break any of the tests that were successfully passing until now. Because that happens all the time. As we go through the semester, at the beginning, no, it's not going to happen often, okay? It's going to be easy because the programs are small. As we get to the end of the semester, some of you are going to start experiencing that regression, where I fix something, but because I fix something, I break something else. So we keep that list of tests on the side. And every time we fix a bug, we go through the whole list of tests again. We try everything on the keyboard to make sure the program works. And then only when that works, all the tests work, then think about refactoring, go fish for another feature. That's it. All right. All the skills that we talked about, so refactor and test are in green because technically I didn't introduce them fully. I just described them at the beginning, right? But all the other skills that we talked about, implementing, you implement your design, you look at a feature, you say, oh, I know how to do this. Okay, implement it. You look at a piece of code that behaves wrongly, you say, I know how to make that loop stop. You implement it. Okay, so implementing skills goes there. What else? Tracing skill, fundamental. You are going to use tracing actually a lot while you are stuck in that debugging loop. Okay, but as a side effect, being better at tracing is going to help you implement better, but that's kind of like a side effect, right? But the most important part is that there is no debugging without tracing, okay? And again, remember what I told you when we learned tracing together? I told you half, again, we cut the brain in half, there's going to be nothing left by the end of the semester, right? But tracing is half of your brain is doing its best to be a robot, to act like a computer, because otherwise you're not tracing, you're just fantasizing about what your code could do, right? And then the other half is desperately trying to get out of the boredom and trying to figure out what it means. What is the code actually meaning? What is it doing? Can I anticipate what's going to come next, right? So that's going to be what you need when you try to come up with that hypothesis about what part of the code is bugged and why is it bugged, okay? That back and forth between the two halves of your brain. Testing, which we are going to talk about in a few minutes. Testing is going to be the art of pretty much extracting a test, meaning that when you have a goal, when you say, I want to implement that feature, what does it mean? What does it mean to implement, for example, a piece of code that reads only positive integer? It sure doesn't mean that we just read integers. It sure doesn't mean that we are going to accept negative integers. So you have to set exact parameters about what are your expectations for your code to be deemed worthy of that part of the requirement, right? So testing here, when you encounter a bug, every bug you encounter, you should have at least one test in your piece of paper on the side that triggers the bug, so that you can be sure that you don't encounter it again. Refactoring, so that one we talk about it real quick, it's easy, it's polishing the code. And then debugging, debugging is this whole thing. Debugging is actually as complicated as writing code. As a matter of fact, the worse you are at writing code, the more time you're going to spend in debugging. That's just the way it is. I cannot fix that for you, okay? If I could fix it, I would fix it for me to start over, right? But I can't. But what I can tell you is the size of the feature that you extract here. The bigger the feature, the more likely you're going to mess that up, the more time you're going to spend in that hell. And then this is how you end up with an exam that's, oh my God, the exam is way too long. Sometimes we mess up, okay? Sometimes I mess up, I design an exam that's too long. Don't worry, handle it. But most of the time, I have some student that feels the exam was way too long, but it's because they got stuck here, and it's not fun. Nobody likes debugging, okay? This is not the fun part of programming. So the only way is to take small features, implement them, something very close to what you've seen before. And then you'll see that you spend less time debugging. And then all of this is almost an algorithm. I almost gave you step-by-step instruction on how to write code. What do we call step-by-step instruction? We call them an algorithm. What is an algorithm? Something that we can implement in a machine. So instead of me teaching you like this how to program, why didn't I just take those steps, formalize them as a real algorithm, implement them in Java or Python or JavaScript or whatever language you like, and now I have a program that can write code. I have a machine that can code itself pretty much. Why didn't I do this? Because this is not an algorithm. This is not defined enough. It's not like a series of step-by-step instructions that you can follow blindly. The main culprit, the main things that actually make this not an algorithm are this one and this one. The other ones, yes, to a certain extent, also I cannot formalize them completely. But design and hypothesis, this is where there's this skill number 6 that we are not going to talk a lot about. I'm going to talk about it like in the next slide, but that's it. The next skill, designing, I have very limited guidelines to give you for that one. I'm not skipping it because it's not important. It's fundamental. If you don't have an idea here on how to implement a feature, you're not going to code. If you don't have an idea when you look at code why it's not working, you're not going to be able to code. But this is a part where we need human creativity. We need your critical thinking, your observation skill, your intelligence, your imagination, all of those things that I cannot formalize as an algorithm, okay? This is pretty much where they shine. And the only way to develop that is to practice. I'm going to give you some guidelines, okay? But they are just guidelines because I cannot give you a step-by-step algorithm to follow to be able to design code or to understand code or to figure out, a bug. That is human intelligence. So that new skill designing that we're just going to mention quickly in passing here, because this is actually the pinnacle, right? So it's definitely human-centered. It's formulating hypotheses. What I'm going to advise you to do is when you are trying to extract a feature, you look for something in the requirement that you have seen before. It could be like the requirement telling you, for example, repeat something 5 times. Repeat 5 times. There you go. I got my micro feature. I know how to repeat 5 times. It's a counter control loop. We've done a bunch of loops. I just need to use my memory, remember what we did, in those code example, implement it, and I have a loop that repeats 5 times. So sometimes you can match one of the requirements to a building block. Sometimes you're going to match a requirement to something bigger than one of those basic building blocks for module 1. For example, part of the requirement will be, I want you to keep reading stuff from the user until they enter the value -23. Well, it's not exactly what I've done in the past, but it's still a sentinel control loop, okay? And I've added a little bit of stuff like an if statement in the past inside of the loop to make sure that I was not, lumping together the sentinel value into my sum, for example. Okay, so now I'm remembering something that is made out of multiple building blocks, a pattern, right? an old example of exercise, something I read in the slide, in the textbook, etc. That's what you're looking for. So you are doing pattern matching. You are scanning through those requirements, trying to find the simplest, smallest thing that you can do next. You get it done, then what is the next thing that is tiny as I can, as simple as I can, that I can do next, okay? Your goal is to make small steps, but always in the right direction. If you do that, you are progressing safely, slowly, but safely, okay? So that's pretty much the main thing about designing. And like I said, building blocks, the concept of building blocks is going to kind of grow now. Module 1, it was only 5 things. Then we started looking at complete example of loops with if statement, like for example, the sentinel control loop with the if statement inside of it so that we don't add the value of the sentinel to our current sum. Okay, that's a new pattern. Every exercise we look at is a new pattern. Every example in the slide is a new pattern. Every example in the textbook is a new pattern. You guys, from now on, you have already your base skills, or you have identified your base skills. You still need to work on them, okay? But you have identified your base building blocks, your base skills. From now on, it's all going to be about seeing more code and not just reading it, okay? Experimenting with code, tinkering with code, getting to remember that code, those little fragments of code that do something useful. And then when you have a problem, you have all of those pieces, like pieces of a puzzle, and you're trying to fit them. You know, does it help me to make a loop to solve that problem? Does it help me to do this? You are trying to really fit the blocks that we learned to the requirement. And then the super important part, select those things to be small as possible, as easy as possible, and then test incrementally, okay? Here's what not to do. Read the requirement, find like a micro feature in the requirement. Oh, I know how to do this. I remember it. Type. Okay, that was easy. Next feature. Okay, that one I remember. That was an exercise. Type. Add some more code, and then what? You're piling up crap on top of crap. Okay, you're like maybe you have like 5 errors in your initial code, which you are going to have errors, and then now you're putting a second layer on top, a third layer. It's like Jenga, but it's really like moving there. So instead, always make sure that whatever small feature you chose is correctly implemented. And yes, in the real world, even in this class, in an exam, sometimes you get so messed up trying to implement a feature that you have to back out of it and say, okay, I'm going to let it be for now. I'm going to choose another small feature from the requirement for now and try to get that to work, right? But ideally, when you commit to a feature, you don't go to the next feature until that one works. If you have to change feature, then undo what you implemented because you don't want bugs in your code. And that's it. So it's all about iteration. Identify a small feature, design a small solution. So my advice to you is 3 to 5 lines. Those numbers are not magical, okay? If you code 4 lines at a time or 2 lines at a time or 6 lines at a time, you're not going to do it wrong necessarily. But I'm trying to give you an idea of how little code you have to add at every iteration of that cycle, okay? Implement your design, test and debug the hell out of it until actually it works, and then go to the next feature. And that's it. And as you implement this, iterative means that you are going to make mistakes. You are not always spinning, like there are 2 loops like that, right, in the process. You're not going to always be spinning here. Sometimes your test fails and you're going to spend some time in debugging. Yes, that's absolutely part of the deal, okay? So those of you who feel bad because every time they write 1 line of code, they have 1 syntax error in it or more, and then every time they get 2 lines of code together with a syntax error, they run it and it doesn't do what they thought it was going to do. Yes, that's normal. That's perfectly normal, okay? You learn to control a device, like a bike for the first time or whatever, you're doing this, right? You're adjusting. Your brain is actually adapting to the new task. After a while, it gets better. Congratulations, you know how to program. That's it. That's all there is to it, okay? So now the question is practice. That's not a question, sorry. Now the point is practice. We are going to have a lot of practice exercise that are going to guide you through this process. Initially, I'm going to scaffold you, okay? So that system where I tell you, get like a small micro feature at a time, when I give you requirements, for the first few times I do that, I'm going to give you the requirements as a block, and then I'm going to tell you, hey, what about you do step 1, step 2, step 3, step 4? So I'm going to guide you through, you should do this much first, then this much after, etc. That's how the next IE is going to be. The next IE is going to scaffold you. I give you requirement and I give you step, like milestones, if you want. I don't want to say step by step because it's not step by step, but it's at least do this feature first. When it works, do that one, do that one. And that's going to help you a little get into the habit of not, trying to do too much in one shot. And then progressively, we're going to remove the training wheels. And you guys are going to look at a block of text that is a requirement. And you are going to decide by yourself, okay, I'm going to implement that feature first because it's small, nice, and I feel I can do it. And then you're going to move on like that. So I'm always curious at that point in the course. We talked about it, right? You guys didn't have yet the practice, but that's what we're going to work on right now. But I want to know pretty much globally how comfortable you are with this idea of breaking down stuff little piece by little piece. So how many people are in this category? Everything's shiny. A few. Okay, not too many, but a few. What about it's easy, meaning that, okay, I get it, but I have to see it work, okay? I have to put it in practice. Okay, well, that's where I expect, most people to be at this point, so perfect. I didn't expect this. I didn't think that we had to do that much stuff for programming, but I kind of get the idea. I just need to apply myself. Okay, very good. Okay, so it's very good to be in that category because that means that you just realize something about this class, about programming. You are breaking all conception, you are getting the new stuff in. Awesome. Last category, who is like a little freaked out right now? It's not easy to admit, okay? But all right, if you are in that category, yeah, that's a lot of new stuff. Okay, but remember, this course is meant for absolute first-time programmers. So even if you don't want to raise your hand or whatever, come to office hours. I guarantee you are in a position where we can definitely get you into this category easily. But we need one-on-one work a little bit. Okay? All right. Practice exercise for this. Write the following programs from scratch based on the requirements provided in the slides. So one side is going to give you the requirement. For example, here, practice exercise number whatever, 3.1, displaying stars. We want to write a program that does this and this. Here's an example of how we run. So you're going to give numbers to that program, a number of stars and a number of lines, and it's going to display this many lines with that many stars in the first line, that many stars -1, then -1 again. So it's all explained in here, okay? That's something that I could use as a question for the next intermediary exam. Something like relatively small, you can get it done anywhere between, well, if you're already good at programming, you're going to get this done in 10, 15 minutes. If you're learning, you're going to probably take half an hour, maybe an hour as you are starting to implement that process that we discussed, okay? And you're trying to take safe steps. And that's it. That's your next IE right there. But in addition to giving you this, I'm going to give you that as well. So when I give you an exercise, I'm going to say, okay, these are the requirements. Get used to them because very soon that's all you're going to get. But for now, for just that next IE, I'm also telling you, you know what? Step 1, you should do this. Then when this works, step 2, you should do that. That. So I do the feature extraction for you. I take like little bite-size, piece of the requirement, and I invite you to work on them. If that bite is too big, break it down yourself, okay? But my point is you should not go from here to here until this works. You should not go from here to here until this works and has been tested, and so on and so forth, okay? So it kind of gives you like a project plan, a milestone list to achieve. And we are going to have a bunch of exercises like that. So here's another one, final countdown, grades average, and I think, here we go, guess secret numbers. So we're at 4 right now. So that one is a little longer, right? The steps are a little longer, they take 4 slides. So we have like 4 practice exercises now for you to work with, okay? And that's it. These are going to allow you to actually put that process into practice. What else? Now what I want to do is I want to take a chunk at least out of one of those skills, Okay, and when we are done with the skills, then we'll go back to those practice exercises. We'll do them together in live coding, if necessary, just to illustrate, okay? But today is going to be one of those talky, not a lot of coding, lecture, where I explain concept. So I told you already about testing, and you can probably see by now the importance of testing, okay? That's what's going to allow you to say, this feature is done, correctly done. Now I can work onto the other one and add more code to something that works, okay? So the reason for which I started introducing testing in my introduction to programming is one, because it has become a very important thing in professional programming, okay? Over the last 30 years, it has become very, very important. And second, is because of that. When I used to ask question to students in the direction of, when is your code working? How do you know when your code is working? I got all over the place answers. Some people told me, I'm not going to run you through the quiz, but some people told me, my code compiles, so why is it not working? Misconception. Compiling just means that you spell checked your novel. It's correct English, but is your novel good? Is it telling the story that you said your editor you are going to tell? No, not necessarily. So the first thing to debunk is that no, compiling is not to be equated with my code is working. Just means it's well written in Java. Okay, you followed the grammar. When it runs correctly on one sample input, oh, I wrote a piece of code. I run it once. One time I ran it and it worked. Trust me. Did you make any effort actually to try to break it? Most of us don't actually. Well, especially when we just write a piece of code that we are really proud of or that was really hard. Hell, we don't want to break it. It's kind of like asking somebody to shoot themselves in the foot, right? So we play with the code, but we play so nicely. We take like a very basic example, a very basic scenario. For example, you enter a number between 0 and 10. I'm going to enter 5. Hey, my code is working. But you do realize that if I use lesser than instead of lesser equal, or greater than instead of greater equal to check that my number is between 0 and 10, this is where the bugs are going to happen, right? If I use the wrong sign, 0 is going to be accepted, which is what I expect, maybe, or it's going to be rejected. 10 is going to be accepted or rejected. So hold on a minute here. What's going on? The goal of my requirement was your program should accept number between 0 and 10. And I tested one of those numbers. So that's not enough. That's not good enough, right? Should I test all the numbers? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Maybe. That would be exhaustive testing, complete testing. I don't leave any chance whatsoever to randomness. I know my code works on the 10 number it's supposed to accept. And then what? Well, it's not good enough to accept 0 up to 10 because you should reject anything that is below 0 and above 10, right? So now I'm testing 11 too. And 11, I expect the code to reject it to be correct. And I'm testing -1, and I expect the code to reject it. Should I test -2, -3, -4, -5, 12, 13? Okay, that's becoming a little overwhelming. So what we are going to learn pretty much to do in this class for testing is we are going to try to strike a reasonable trade-off. It's generally not enough to say my code ran on one test that I came up with, so therefore my code is good. No, generally it's not enough. Running it on every possible input, very fast, we're not going to be able to do that. Even for small program, there's just too many things that you could input. This is not a good idea, etc. Running when I cannot find a sample input on which it fails, yeah, that's kind of where I want you to start thinking, except that you could be lazy and you could say, I'm picking D, right? But I'm going to just do one test. Nah. So we have to have like a sort of trade-off. You have to use enough testing for each feature that you can be reasonably confident that your code implement that feature 100% correctly. And the operational keyword is reasonably confident. This is like very subjective, right? That's real word, okay? So that means that we cannot prove, for most programming tasks, we cannot formally, mathematically prove that our code is doing what we think it's doing. It's just actually a very hard problem for computer scientists, people that are in the theory of computation, okay? What we can do is we can prove that a program is wrong, right? So if I write a piece of code and I show it to you, and each one of you, for example, there's a prize or something, right? Or bragging rights if you find a bug in my code. Each one of you is spending 1 hour trying to break this code to find the one situation where this code is not going to work. At the end of that 1 hour, with like about 30 people, looking at my code and trying their very best to break it. I cannot promise you that this code is correct. Maybe all of us are wrong. Maybe we all overlook something. It happens. But I can increase my confidence that we did everything we could to try to find the flaws and the bugs in that code, right? So my confidence to take that piece of code and go present it to my boss, for example, is going to be good enough. And of course, if your team is bad, right? If nobody in the team can see bugs, etc., then you are going to go through that testing process, and the testing process will not be good enough. So all of this is hinging on the fact that you test enough and you get better progressively at testing. So you really try to break the code with reasonable force, pretty much. You apply reasonable force to try to break that code, okay? So that's all we can do. We cannot mathematically prove that our code is working. We cannot look at a series of tests and say, now that my code is passing all those tests, the feature is 100% correct. All we can do is try our best to find the hardest test and survive the test. Now I can say I'm more confident that my code is correct. It's kind of weird. How many of you anticipated that there would be that kind of subjectivity in programming? Anybody anticipated actually that you would be able to prove that your code is working, like mathematically or something like that? No? Okay, if you didn't anticipate that, you had good intuition. Okay, definitely. But sometimes it's a little counterintuitive. So that's why I'm stressing it out here. All right, so what are the guidelines that we're going to use through that subjective problem to try to get us a good testing habit? Two things at the menu. One, we are going to use tests to formalize ambiguous requirements. So we are going to use tests to pretty much rephrase the requirement. Somebody comes with a bunch of requirements to me. I'm going to translate those requirements into a series of tests. And then I'm going to go back to my client and I'm going to show them, so I read your requirements. Come here, have a seat with me and let me know if this is the right way to understand your requirements. When the program received this data, you wanted to output this data. Yes? Yes, okay. So first test is correct. When the program received this data, you wanted it to behave this way. And we're going to go through a list like that. So what I'm doing is I'm translating the requirement that can be more or less, fantasist or whatever, ambiguous, and I'm translating them into like a table. We're going to call that a test table, where at least for every bit of input, so each column is going to be one source of input, like variables that you type, etc. This is what I expect the program to do. That's one test. For those input, I expect the program to do. When the player goes right, I expect the screen to scroll right. When the player goes left, I expect the screen to scroll left, etc. Stuff like that, right? And we are going to turn that into a document, a test table with a bunch of tests. And when the client and I agree that those tests actually capture everything that the client had in mind and wrote in the requirement, then we can get to work. So it's not unusual to use tests before even to code, to just get an idea of what your code should be doing. And you can use that also in an exam. You can read the exam 2 or 3 times, the requirements, right? You can read it 2 or 3 times and start thinking, okay, this is the first feature I'm going to go for. I'm going to write down 1, 2, or 3 tests that are going to help me make sure that this feature is correctly implemented. And only when you're done doing that, then you start talking about, I'm going to code now. Because as you code, you're going to test your code with those tests that you already designed, okay? So that's the first thing that we are going to do with tests. The second thing we are going to do with tests is ensure code coverage. So code coverage is a technical term that just means if I have 100 lines of code, I need to make sure that when I'm done running those 100 lines of code through all of my tests, Each and every one of those 100 lines of code has been at least tested once. You cover your code. Your test together as a test harness or a test suite, as we call it sometimes, they cover all the possibility of execution of your code. It's very important. So that there's not like a little hidden feature in your code that's going to trigger at the worst possible moment and make, for example, a rocket go down. This is what happened with Ariane 5, I think, like decades ago. Anyway, so how do I find an example that drives home the idea of, formalizing test, a formalizing requirement is actually a thing that's necessary? We need a very simple problem. So I found a problem that's supposed to be solvable by 8 years old and above kids. So that should be okay for us, right? I'm using a board game. And for the last 3 times that I taught this class, I had to make a side note here. Yes, the name of the board game is Pandemic. This is not a crack about COVID. This is just actually a cooperative board game that I used for years before we actually had a pandemic to deal with. So my apologies if you find this a little, cringy, but yeah. So this is a board game. This is a cooperative board game. The players are all coming together to try to beat the game or to beat one of the players that plays a bad guy, okay? And it's meant for 8+ years old. So technically, 8 years old can pick that up, read the instruction, and play the game, okay? And somewhere in the instruction of the game, for one of the variant, it says something like the bioterrorist player. So this is a variant where, 3 friends are going to play against one that plays a bad guy, the bioterrorist. The bioterrorist player takes a turn after every player. And that's it. That's pretty correct English. Nothing to say about that. It's okay. It's pretty understandable. Except that, for those of you who don't know that, there is a forum called Board Game Geeks that is actually dedicated to board game and stuff like that. This line in the instruction caused actually a lot of traffic on the Board Game Geek forum. People were asking, so I don't get it. Is it the bioterrorist player takes a turn after every player, meaning you take your turn, I take my turn, I'm the bad guy. You take your turn, I take a turn again. Is that what you meant? Or did you mean every player, let's say the 3 of us are playing, right? Every player is going to take a turn, and then the bioterrorist is going to take a turn. This is a commercial product meant for 8 years old. There was no doubt that this has been reviewed, redacted, proofread, whatever you want to call it, right? This was polished. And a bunch of adults go on the internet, on the forum, where what adults do on the internet anyway is not a big landmark, but anyway, they go there and they ask for clarification to the point that the next edition of the game is rephrased to say the bioterrorist player takes a turn after each player. That's a little better. There's no room for ambiguity. And between parentheses, just to put the nail, into the coffin after that player's whatever step in the game, right? This is what I told you when I said it's harder for me to write an exam than to write a piece of code. Maybe not generally, like there are problems that are really hard to solve, but I mean, in this class, it's harder to make it so that the instructions are completely unambiguous than actually just writing the code that does this job. And that is something that's going to be there always. Again, while we try in this class, or I try and the TA helped me, we really try our best to make the instruction completely unambiguous. This is definitely something that could happen. How do you handle it? It's your final exam. You have 2 hours, you're on the clock. You see 2 possible interpretations. The only way to handle it is to document as a comment in your code. I saw 2 possible interpretations. I'm going with this one and explain why. And then, even if you did something that we didn't anticipate, at least if you had a good reasoning behind it, we'll try to give you partial credit, right? But the idea is that, yes, trying to figure out what is expected of you, even in case of ambiguous statement, is part of the programmer's skill. In real-world scenario, you go back to the client, you ask question. You ask question to your instructor during the final exam, stuff like that, right? So you communicate to fix the problem. This is going to happen more and more to you as you go up in programming classes and get closer and closer to the real stuff, okay? Concept of code coverage. Well, why is it bad if I don't cover my entire 100 lines of code with all my tests, okay? Well, it's bad because, so tell me more about that code that your tests never get to run. Is it useless? Your tests are supposed to represent the requirement, right? So I have those 10 lines of code in my program. No matter which test I run, they never get executed. So what are those 10 lines of code doing there? The test captures the requirement. Those 10 lines of code are not triggered by the test. Therefore, those 10 lines of code do not capture the requirement. So what is it, an Easter egg? The name of the programmer will display, if you do up, up, down, down, left, left, or whatever. Okay, so yeah, if it's an Easter egg, that's legit. But other than that, you have dead code. You have code in your program that's never going to get executed under normal circumstances. And this is actually the kind of bug that caused, like I mentioned, Ariane 5 was a rocket launcher, a French rocket launcher like decades ago. This is exactly what happened. They had a version of the code for Ariane 3, then Ariane 4, they didn't use that code anymore, but it stayed in the code base. Ariane 5, for whatever reason, a specific condition triggered that code to be executed, but nobody had maintained that code for like 2 generations of launchers. So pretty much that code triggered, nobody expected it, nobody even remembered that code was there, and boom, the rocket went actually and exploded, okay? So if your code is not useful, get rid of it. If your code is useful, then test it. If you do not test it, then you're not actually programming. You're just writing random code. There are different ways to measure code coverage. And if you actually Google the idea of code coverage and stuff like that, you're going to see that there's a lot of debate about whether code coverage is really that useful. So we are not going to enter that debate. I'm not going to tell you having 100% coverage of your code is always necessary. Because in real life scenarios, sometimes it's not. It's a little complicated, but sometimes it's not, okay? But what I'm going to tell you is for this class, because of the size of the programs we do, they are generally small to medium sized programs. In this class, you must always achieve 100% code coverage with your test. And sometimes, it's going to go very naturally. Sometimes you just pick a feature, you come up with 1, 2, or 3 tests for that feature. And at the end of the day, you look at all of your tests, you look at all of your lines of code, and you realize, yes, when I run my program through all those tests, everything was used at least once. And most of the time, it's going to be natural like that. Sometimes, after you're done testing your features, you're going to realize that there is one of those dead code zone, in your program. Then you're going to think about it. Do I really need that code? If so, what additional test should I put in my test harness, to test it? So make sure that you understand, okay? I'm not saying that you always need 100% code coverage with your tests in the real world, but for this class, definitely. That's going to be one of your guidelines. Did I test every feature? And did I test every part of my code? So let's take a look at counter control loop. Whenever you have a counter control loop, and actually this is one thing, I don't remember, I'm sorry about that, but I forgot who made that remark, but somebody either in the morning or afternoon session made actually a remark or asked a question that was exactly in those lines. Their logic was, I could tell that their logic was, I have a loop, what can happen? Maybe I cannot enter the loop, never. Maybe the while condition is false, to start off with, or maybe I never get out of the loop. So they were starting already to think in terms of, what can possibly go wrong. That's exactly what I want you to do when you test. So if you are given a counter control loop, is it possible for the loop to run 0 times? Like I cannot even get in because the while condition is false to start off with? I should pay attention to that, okay? Should it work actually at least 1 time? So maybe I should have a test that makes it never start, a test that makes it start 1 time, go through 1 time. What about the maximum number of iterations I should expect? These are like vague questions, I know, but this is just to give you an idea of what to think about, right? So now you're trying to say, can I not start it? Can I go into an infinite loop? What is the maximum number expected, etc. And you are going to build tests. So for one counter control loop, you can have like 4 or 5 tests like that. It's very, very possible. Do you remember when we had a counter control loop and I changed a less or equal to a different, and suddenly it went 2, 4, 6, but the condition was if n, whatever the variable was, is different than 5. So while n different than 5, that made my loop go infinite. We've seen that bug one time together, the slides. Now it's there somewhere. When I said sooner, you are going to, now that you have the basics, now you're going to start just learning more patterns. Every time you encounter a bug, it should like leave something in your head a little bit, or even a vague recollection, because then this is what you're going to think about testing when you are facing similar code. I saw plenty of things go wrong with counter control loops. So if you give me a counter control loop, if I'm grading you, for example, I'm not going to just like read your loop like with a blank mind. I'm going to read your loop and try to project on it all the bugs that I can think of. I'm going to do test. One bug, one test. That's how you're going to make sure that your code is actually rock solid. So different things can go wrong, right? The skip over the value detected was one. If I was incrementing my counter, but I really need to decrement it, that would be also a bug. So I pay attention to those things because I've been burned before. Okay, been burned. What about sentinel covered loop? Very similar. Very, very, very similar. Always the worry of, am I going to go into an infinite loop? Can I even get into that loop? Is it even possible to get into that loop one time? Should I get into that loop one time? And then with the sentinel control loop, there is a little variation that we saw also as a bug together. Do you remember that program that was reading positive value from the user and adding them up? And then when you enter -1 at the end to say I quit, it was taking the -1 and adding it up to the sum. That's not what we wanted. So now that you have encountered that bug one time, and we took our time, we talked about it, etc., it should be in there forever. Now, when you see a counter control loop, you think about those bugs. When you see a sentinel control loop, you think about those bugs that you encountered before. The truth about it is what I tell you about in the lecture, about 60, 70% is flying like this. I know I was a student too, right? But when you practice and you spend half an hour on a loop because of a silly little bug, like one character to change sometime, and when you finally find your bug after spending half an hour, you finally find the bug and you remember it was in the lecture, that anger that you're going to feel maybe, this is going to be what's going to etch that knowledge in your brain forever. There is nothing that beats getting frustrated by a bug to the point that once you're done and you finally solve it, you swear to yourself, I'm never going to fall for that again. Okay, so yes, I tried to give you a heads up during the lecture. We all know that lecture, there's a lot of information. Some of it is going to slip by, but when you practice and you get into bugs, this is when you are really going to get that. And we're going to stop here. Okay, we're going to stop here because there's a lot more stuff to do and we're running out of time. So thank you for your attention. And if you have questions, I'm going to hang around a little bit. So don't hesitate to come and see me.